Okay. Hello, everyone. We'll come back to this problem in a few slides. Let's start out with course announcements. Just a reminder that there are office hours for Vincent tomorrow at 10:30 and for me at 10 a.m. on Friday, both Montreal time. And that problem set 3 will be due at the end of the day on Friday, so 11:59 p.m. Montreal time. A reminder that if you use theorems on the homework, you should prove them unless they're common sense. And for a fairly liberal notion of common sense, but yeah. In particular for the conditional probability, just don't worry about it. Again, on the conditional probability problem, if you're proving those things, it's not really important to be extremely rigorous with your proofs. The goal of that particular problem is that you work out whether something is true or not true, and if it's not true, come up with a counterexample, rather than having the proof should be one sentence. You can use any theorem without proof if we've stated it or proven it in class. Regardless of whether it has a name, you can say, we proved this in class. Are there any questions? Along those lines for problem 4, can somebody is not muted. Can you mute yourself, please? Thank you. Along those lines for problem 4 is the question, can we assume that we are dealing with discrete things? So probability distributions over discrete valued random variables, yes, you may assume that if you wish. It's not going to change anything, but yes. Were the solutions to problem set 2 posted? Sorry, they're going to be posted tonight. Sorry, that's my fault for not for taking a while to look over solutions. I wrote the solutions last time. Vincent wrote the solutions this time, and sorry, I haven't had a chance to work with him to finish that up. Okay, let us move on to linear programs. Let's start out with hyperplanes. So hyperplanes, we've already seen a little bit, but let's take a look at this again. So the equation of a line in two-dimensional space, vector space, can be expressed as ax plus by equals c, a, b, and c being real constants. Similarly, a plane, if you're in 3 dimensions, can be expressed as ax plus by plus cz equals d. So here's an example of a plane. A hyperplane is just a higher dimensional analog. It is just the set of points that satisfy a single linear equation between all of the variables and the constant term. So a line is, for example, a 1-dimensional hyperplane in 2-dimensional space. A plane is a 2-dimensional hyperplane in 3-dimensional space, and so on. It's hard to visualize some of these things in higher dimensional spaces. I might have said this. I don't remember if I said this before. When a mathematician is trying to visualize a very high dimensional space, we tend to visualize like lower dimensional spaces and then just pretend that we're visualizing a higher dimensional space. I definitely don't have a good conception in my mind of what R10 looks like. Why is it true that the vector, if you consider this coefficient vector, is the perpendicular vector to the hyperplane? So for example, here, if you have a plane, then the perpendicular vector to it is ABC. Every hyperplane has exactly one vector that is perpendicular to the whole thing. If you're in 2-dimensional space, there's a line and there's a perpendicular line to it. If you're in 3-dimensional space, there is a plane and there's a vector perpendicular to it. Why is it true that the vector, which is perpendicular to the plane, is the same as just the coefficient vector, ABC? I remember learning this in high school and having no idea why it was true. Yes, we definitely want to show that a dot product is 0. 2 vectors are perpendicular if the dot product is 0. Now, the tricky thing is that you have to remember that the dot product with just a vector x, if the dot product of a and x is b, it's not 0. But what does it mean to be perpendicular to the plane? Does it mean that you're perpendicular to every x which is in the plane? Yeah, so what it means is that it's perpendicular to any vector that actually lives inside the plane. And so a vector that lives inside the plane, we can think of as the vector between 2 points, x and x prime, on the hyperplane. So if you have x and x prime on the hyperplane, that'll give us the choice of any vector within the hyperplane. And so the vector between them is x minus x prime. And so how do we show that this is perpendicular to A? Well, we know that A dotted with x is B, A dotted with x prime is B. So A dotted with x minus x prime is B minus B, which is 0. Which means that A and x minus x prime are perpendicular. So if you go back to this picture, you can see that if you take any 2 points in the plane, then that will point in a direction which is perpendicular to your vector. So this is called the normal vector to the plane, or the hyperplane in general, because it is perpendicular to every vector that lives within the plane. Are there any questions about this? So often you'll hear people sort of refer to hyperplanes by their normal vectors. We'll go back and forth between a sort of geometric interpretation of linear programs and an algebraic notion. And they're both very helpful. Okay. So convex sets. We're not really going to use convexity, but I wanted to include it for the sake of completeness because it is an important thing in thinking about polytopes. So a convex set of points in Rn is just a set such that if you have any 2 points in the set, then every point on the segment between them is also in the set. And you can write any point on the segment between them as a weighted combination of one and the other, where the weight is between 0 and 1. So for example, this is a convex set because for any 2 points in the set, if you take the segment is completely contained in the set. If you take the this set which is non-convex, there is a set of 2 points where the segment goes outside the set. So these points would correspond to some W which don't work. Okay. Here are some more examples. These ones on the bottom are not convex because if you pick 2 points, there are some 2 points where the segment doesn't lie completely inside the set. These are all convex on the top. Are there questions? It's the same thing, basically, as when we were talking about convex functions. It's just, yeah, good timing for that question. It's the same thing as when we were talking about convex functions. Remember, a convex function is something that's always curving up. So if you think about filling in all the area above a convex function, that gives you a convex set. So for example, a parabola is a convex function. So if you imagine like pouring something into a parabola, so that like you fill up all the area above the parabola, that is a convex set. Though also a concave function is just the same thing upside down, where it is actually a convex set if you fill everything below the function, which is, yeah, a bit confusing. So both convex and concave functions will give you convex sets. For convex functions, it's everything above the function. For concave functions, it's everything below the function. You shouldn't ever talk about a concave set, though. That's not, you just a convex set or a non-convex set. Questions? Okay. Polytopes. Oh, there's a question quickly. When we look at these plots of sets, is there an intuitive way of relating the shape to the domain or range of a function. So not every set corresponds to a function. For example, this set is not, you would need several functions to express it because it's not the graph of a function. Here, I mean, you also would need like a function which is sort of the upper half and a function which is the lower half. So not really, but sort of yes. I'm not exactly sure what the question is. Okay, polytopes. So to get to a polytope, we have to define what a half space is. So a half space is basically just like one side of a hyperplane. If you imagine like chopping all of real space in half with your hyperplane and then filling in one side, that's a half space. So it's infinite, going off in one direction. It's just the same thing as a hyperplane equation, just with an inequality instead of an equality. So it could be either less than or equal to or greater than or equal to. And so a polytope is the intersection of a finite number of half spaces. This gives us a connected and convex set. Connected means that you can get from any point to any other point going through the set. Convex is just what we saw. And I'm not going to prove that that's the case, but basically the reason why it is convex is because the intersection of convex sets should give us another convex set. So here we have shaded in the half spaces. Though theoretically, this should go out to infinity in these three directions. And this fully shaded triangle in the middle is a polytope. It's the intersection of all of these half spaces. So a polytope is like, it is a generalization of what is referred to in common parlance as a polygon in 2 dimensions and a polyhedron in 3 dimensions. Polytopes can be in any number of dimensions. So this is a polytope. It's also a polygon because it's in 2 dimensions. This is a polytope, but it's also a polyhedron because it's in 3 dimensions. And you can see that these are all just the intersections of half spaces, because you can imagine each of the sort of facets of this polytope being one of those half spaces. If you imagine sort of extending this out to infinity, then this gives you a hyperplane, and each of these other facets gives you another hyperplane. And if you look at one side of that hyperplane, then that's a half space. Polytope does not have to be finite. You could end up having the polytope going off to infinity in one direction. Single half space is polytope. Polytope can also be empty. The intersection could have no points at all. Questions? Yes, polytopes can be empty. There can be no points in a polytope. That would be if these if these half spaces do not intersect. For example, if you had a half space which is everything over here and a half space which is everything over here, just never intersect. Okay. So in that case, how is the set convex? Well, for every if it's an empty set is convex because for any 2 points in it, the segment is contained in the set, because there aren't 2 points. But if you could pick 2 points, then the segment would be contained in the set. I know that sounds sort of glib, but that is completely correct. Same thing with the entirety of the whole space. Like all of R to the n is also convex because it can every 2 points within it, the segment is fully contained in it. We're probably not going to deal with those edge cases very much. Like I'm not going to. Yeah, you won't have to worry about like empty polytopes, except in infeasible linear programs, which we'll get to in a moment. But yeah, you don't have to think of them as empty polytopes. Okay, so there's an entire field of math which concerns itself with studying polytopes. So discrete geometry is often concerned with studying polytopes. And they are super useful, as we will see when we get to linear programs in a few slides. So it has a lot of relevance for like optimization. But there's also just really beautiful math involved. So some of the definitions here that we will be talking about, but also are just interesting, are so a vertex of a polytope is a point. A vertex is like that thing that we always call a vertex for a polygon or a polyhedron. It's intuitively that thing, a corner, right? So what actually is it? Well, if you think about these as intersections of half spaces, well, a vertex is just a point that lies simultaneously on n of the bounding hyperplanes. So like, for example, this is in R2. So the vertex is going to have to lie on this hyperplane and this hyperplane. So that's two hyperplanes. It's an intersection between two of the bounding hyperplanes. So here's one vertex, here's another vertex, here's another one. This is also an intersection between two of the bounding hyperplanes, but it's not in the polytope. Sorry, I should have said is a point in the polytope. So a vertex is any of the points that are in the polytope and lie on n of the hyperplanes. And the question about a name for a soft polytope, I'm not sure I quite understand what that means. Could you clarify in the chat? Okay, so we've seen vertices. What are edges? Well, I mean, edges are just the edges of the polygon or the edges of the polyhedron. But what are they technically? Well, it's very similar to a vertex, except it's the set of points in the polytope that lie simultaneously on some n-1 of the bounding hyperplanes. So for example, if you pick this hyperplane, then the set of points in the polytope that lie on this hyperplane is an edge. If you go to 3 dimensions, then you say, okay, well, what are the set of points that lie on this hyperplane here and this hyperplane here? Well, it is the set of points in the polytope that lie on both of these hyperplanes. It is this edge. And the reason why we picked 2 hyperplanes is because it's n-1, the dimension -1. And so in general, you can think of a d-dimensional face of the polytope as being the intersection of n minus d of the bounding hyperplanes with the polytope itself. So if you were in a 10-dimensional space, then there would be 4-dimensional faces where you took the intersections of 6 different bounding hyperplanes. I know that's hard to visualize. There is one particular, so all of these are faces. Vertices are 0-dimensional faces. Edges are 1-dimensional faces. And then if you go to sort of the highest possible dimension before you get the entire polytope, a facet is an n-1 dimensional face, which is just a set of points in the polytope that lie on one of the bounding hyperplanes. So here, a facet of this polyhedron is just going to be one of these, the intersections of hyperplanes with the polytope itself. This facet, this facet, this facet, this facet, and so on. And in the case of 2-dimensional polytopes, a facet is the same as an edge, because 1 is equal to n-1. A face is the general term. So vertices are faces, edges are faces, facets are faces. Vertices are 0-dimensional faces, edges are 1-dimensional faces, facets are n-1 dimensional faces, and then everything else you sort of just call like a 2-dimensional face or a 3-dimensional face, or yeah. And then there's an n-dimensional face, which is just the whole thing, it's the whole polytope. And the reason why these things, like, if you're interested, there is this thing called Euler characteristic, which will tell you about like the sum of the number of faces of different dimensions. If you take like the alternating sum, the number of odd dimensional faces minus the number of even dimensional faces, this will be like Euler characteristic. It's next to the Euler characteristic. Anyway, so you might have seen this if you ever saw like planar graphs of like, edges plus 2 minus faces minus vertices, something like that. This is the general formulation for polytopes in any dimension. But anyway, we're not going to get into that. But there's a beautiful theory of math involved in that. The question: if instead of hard decision boundaries for being in the set, they were probabilistic? Oof, I don't have a simple answer there. I'm sorry. It's a good question. So another Way to think about a polytope is as the convex hull of its vertices. So what is a convex hull? A convex hull is just the smallest set of points that contain, is like a convex hull of a set of points is the smallest convex set that contains all of those points. So for example, if you have these 6 vertices, what is the smallest set that is convex and contains all 6 vertices? Well, it's this polytope. It's the polygon with those points as its vertices. In 2 dimensions, you can think of this as basically like stretching a rubber band around those vertices. And in higher dimensions, you can imagine like stretching, like, I don't know, like cling wrap around all of the vertices in a higher dimensional space. Or like, yeah, like having a balloon that's trying to contract around all of those vertices. So that's what a convex hull is. And a polytope is also a convex hull. I'm not going to prove that, but it's pretty easy to prove. Questions? So let's start out with some nice examples of polytopes. So the polytope with vertices 0, 0, 1, 0, 0, 1, and 1, 1. That's just a square. I'm going to let you imagine that. If you take all the possible vertices in 3 dimensions with 0 or 1 in each coordinate, then you get a cube. If you do this in higher dimensions, you get what's called a hypercube. This is as good as we can get as a way to draw the hypercube that is a 4-dimensional thing. Sorry, the hypercube in 4 dimensions in 2 dimensions. It's sort of hard to do. But there are hypercubes in every dimension. You can go up to like 5 dimensions, 6 dimensions. How many vertices does the n-dimensional hypercube have? Two to the n, because there are 2 choices for each of the n coordinates. 0 or 1. Cube has 8, square has 4, and then the hypercube in 1 dimension is just 2 vertices. How many facets does it have? Remember, facets are like the n-1 dimensional faces. Think about small examples. How many facets does this have? Well, it has 1, 2, 3, 4. Here it has 1, 2, 3, 4, 5, 6. I'm not going to look at dimension 1 because that's a little bit weird to define. But it still does have, it has 2 facets actually, because the facets are just the 2 vertices. Yeah, so it has 2n facets. And the reason, what are those facets? So here it has, the number of facets is like 2, 4, 6. Here it has 8, and so on. What are the facets? Well, the facets are just that xk, each of the coordinates, has to be greater than or equal to 0 and less than or equal to 1. Those are the 2 sort of sandwiching facets. And then there's one of those for each of the n dimensions. So 1 pair of them. So you have 2n facets overall. Interesting thing, you can have way more facets than vertices or way more vertices than facets. In fact, what you can do, there's like this, you can take the dual of a polytope, which is not going to be the same as, we're looking at a different kind of duality, but one can take the dual of a polytope, and that basically corresponds to swapping vertices and facets, which means that you take like the center of each of these faces as a cube and you connect them and you get another polytope. This is not something that we have to think about now, but yeah. If you do that, then you end up with something that has 2 to the n facets and 2n vertices. Okay, now we've seen the hypercube. What about the simplex? This is the other good example of a polytope. So the regular simplex is the generalization of the equilateral triangle and regular tetrahedron into higher dimensions. Here's a triangle, here's a tetrahedron. One can think of the n-dimensional simplex. It's easiest if you want to sort of think of it in a coordinate space, to think of it in actually one higher dimension. It's a little bit weird. So here you can think of the equilateral triangle as the point zero, as the convex hull, sorry, of the points 0, 0, 1, 0, 1, 1, sorry, 0, 1, 0, and 1, 0, 0. It's just the coordinate vectors. So this is clearly an equilateral triangle. If you went to four-dimensional space and you connected all the four points like this, you would end up with something that is actually a regular tetrahedron. I know it's hard to visualize, but basically it's just because of symmetry. How many vertices does the n-dimensional simplex have, which you can visualize within R to the n plus 1? Again, this is the triangle is a two-dimensional simplex. The tetrahedron is a three-dimensional simplex. In each case, we have one vertex more than the number of dimensions, which makes sense because we can visualize it in R to the n plus 1 with that number of vertices. How many facets does it have? Disagreement. Look at the smaller cases. How many facets does this have? 1, 2, 3. How many facets does this have? 1, 2, 3, 4. It is also n plus 1 facets. Remember, this is a three-dimensional simplex, has 4 facets. 1 is opposite each of the vertices. And it's pretty easy to work out what the equations of the facets are if you use this embedding in R to the n plus 1. There's just like, there is a very simple equation of just like sum of the coordinates summing to 1. But 2 has 2 facets. No, 2 has 3 facets. 1, edge, edge, edge. So there are 4 facets of a tetrahedron, 3 facets of a triangle, and so on. I realize this may not be extremely useful like immediately, but this is sort of just a way to think about higher dimensional polytopes. And I think it is useful if one is trying to get a deeper understanding of what is going on with linear programs. Okay. Now let's actually look at what a linear program is. So a linear program is an optimization problem maximizing or minimizing a linear function of variables given linear equalities and inequalities as constraints. So for example, you could be minimizing this function, linear function of the variables, subject to these constraints. With equalities, greater than or equal to, less than or equal to. You could also have a maximization problem. Yeah. Questions? Okay. Are these primal and dual? No, these are not primal and dual. They're just different. We'll get to primal and dual. Feasibility. So a feasible point of a linear program is any point x that satisfies all the constraints, but it might not be at the optimum. Okay. So since we have a bunch of linear equalities and inequalities, the set of feasible points is a polytope. Yay. So if you go back to any one of these linear programs, then you have a set of constraints, and this will define a polytope. So this might be your set of feasible points, or this might be your set of feasible points. the dimension of the polytope might be lower than the dimension of X. For example, if there are lots of equality constraints, then you could end up sort of saying, OK, I'm in this lower dimensional subspace of R to the n. So for example, this triangle simplex lies in a plane in R3. So the dimension of the polytope doesn't have to be the same as the ambient dimension of space. If there are no feasible points, so here's where the empty polytopes comes in, then the NLP is said to be infeasible. No possible solutions. Not only is there not a good optimum, there isn't anything that could be optimized over. So if the LP has an optimum, it occurs at one of the vertices of the polytope of feasible points. Why? We're not really going to prove this, but let's just see the intuition behind this. And yes, it also does have to do with convexity. Suppose we must maximize, suppose it's just a maximization problem. We're maximizing some linear function of the variables. We can express that as a dot product, c.x, for x in R to the n, and for some, c is also a vector now in R to the n. So you can think of this as a dot product. So why is this interesting? Well, we can think of a dot product as a projection. We can think of it as we can think of a projection in the direction of C. So if you have a vector A and you're dotting it with a vector B, you can think of this as the magnitude of A times the magnitude of B times the cosine of the angle between them. And if the magnitude of B is 1, so if you think of B as just a direction, then it's just A magnitude of A times the cosine of the angle, which is just the projection onto B. So you can think of this as the projection of X onto the direction of C. How much of X is going in the direction of C versus going in another direction. You could make this more rigorous. You just scale C. You divide C by its norm. It's equivalent to maximize c.x over C over the norm of C. I guess I should have said that. So how do we maximize the projection of X in the direction of C? Well, it's just like, how far can we go in the polytope in the direction of C? So if we're optimizing with an objective of c.x, we're just looking at how far can we go in the direction of C without leaving the feasible region, without leaving this polytope that is the set of feasible points. And if we imagine sort of going in any directions, like pushing a line until it tries to leave the polytope, it is going to occur at a vertex. And I'm not going to formally prove this, but just having the geometric interpretation of this, it makes it a lot more convincing. So this has to occur at a vertex. It might not just occur at a vertex. If you picked an objective function which was exactly perpendicular to this edge, for example, you would end up having all of the points on this edge of the polytope be maximizing the objective. So you could have a whole edge or even a whole facet of the polytope be the optimum. But it does have to contain at least one vertex. There is a vertex such that it is maximized. And just for generic directions, unless you happen to pick a direction which is like perfect to sync up with one of the edges or other faces, high dimensional faces, then you're going to end up with just a single vertex. Are there questions? Sometimes there isn't an optimum if the polytope is unbounded. For example, here's an unbounded polytope. It's unbounded in some directions. So if you tried to just optimize in this direction, you would never find an optimum. But there are optima for linear programs if you define the optimum, the objective is going in a different direction. If the polytope is completely bounded in every direction, then there are optima in every direction. So for example, if you had an LP on the simplex or the hypercube, then you would end up with an optimum all the time. Let's go back to the problem that we had at the beginning of class. Suppose that you have two vectors in R to the n with c fixed and v variable under the constraint that its L1 norm is at most 1. Let's prove that the maximum value of c dot v is attained at some v where all the entries are 0 except for 1 plus or minus 1. Why is this true? How could we start doing this? What is the set of v in R to the n such that the L1 norm of v is less than or equal to 1? It's not actually a simplex, and it's not a triangle in 2 dimensions. Let's remind ourselves what this is. The constraint is that the sum of the absolute values is less than or equal to 1. So we can rewrite this as plus or minus, sorry, I should have taken out the absolute values here. Plus or minus v1, plus or minus v2, plus or minus vn is less than or equal to 1. So you have 2 to the n different inequalities. And yeah, as people were saying, in 2 dimensions, it looks like this. You have a square, but it's a square that's tilted. It's a diamond. In 3 dimensions, you have the 2 to the n inequalities defining this thing that you might recall is called an octahedron. In general, it is called a cross polytope. For n dimensions, it is a cross polytope. The 2-dimensional version of a cross polytope is the diamond. The 3-dimensional version is an octahedron. And then you just call it the cross polytope. If you remember what I was saying about dual polytopes, and again, dual polytopes, not the same as dual linear programs. Dual polytope is if you take the center of each of these facets, you get the hypercube. So the cross polytope is actually dual to the hypercube, which means if you take the center of every one of the facets of this thing, you get a hypercube. If you take the center of every one of the facets of the hypercube, you get this thing. So you can swap between them. Can I explain why there are 2 to the n inequalities? Yes, absolutely. I'm sorry, I messed this equation up. There shouldn't be absolute value signs. What this is just saying that you can rewrite the constraint that the L1 norm is less than or equal to 1 as all 2 to the n possibilities for this. You can pick plus or minus for this one, plus or minus for this one, plus or minus for this one, plus or minus for this one. So for example, in 2 dimensions, you have x plus y is less than or equal to 1. X minus y is less than or equal to 1. Minus x minus y is less than or equal to 1. Minus x plus y is less than or equal to 1. So that's just the equivalent statement to saying that the L1 norm is less than or equal to 1. Now, this is why L1 norm regularization works. Because what are the vertices of this polytope? Like, what physically are the vectors? Like, how could we write them down? What are these vectors? Yeah, they are the basis vectors for the space, plus or minus, or you could think of them as like plus or minus one-hot encodings if you are into machine learning, for example. The vertices are this. And so we already know that the maximum has to be attained at one of these points, the maximum of the this linear program, which is maximize this linear function of the variables subject to these inequality constraints. This is showing that if you are trying to do a thing subject to constraints in the L1 norm, you're going to end up with something that's sparse, which is really interesting. This is why L1 norm regularization, for example, is used in, say, neural networks, but in other contexts as well. It gives you sparsification. Optima are likely to find one of these vertices. So you're likely to end up with something that has a lot of zeros. Questions? Okay. So there's a standard form for a linear program, and this has the optimization as a max, not a min. I'm not going to find sparsification, sorry, because that's not something that is really within scope for today. I'm happy to chat about it later. Oh yes, question here. It doesn't say that these are the only maxima. That is correct. It could be maximized on an entire edge or an entire face, but it just says the maximum is attained at one of the vertices. Could be more than one of the vertices, and it could be some other points as well. Good question. Yeah. So standard form of a linear program has the optimization as a max, not a min, has all variables constrained by xk greater than or equal to 0, has all other inequality constraints as less than or equal to, not greater than or equal to, and it has no equality constraints. So we can convert any LP into an equivalent LP in standard form. And here is how we can do it. How do we deal with 1? We can just negate the objective. We can flip the signs of the coefficients in the objective function. For example, the min of this could be the max of the negative of it. How do we deal with constraint number 3? I'm going to come back to 2 in a moment. Similarly, we just flip the constraints. You can negate them, and that changes the direction of the inequality. What about 4? We don't want any equality constraints. How can we get rid of all the equality constraints? We could write it with slack variables, or just one way to do it is just to do two inequalities. An inequality going one direction, and an inequality going the other direction. And notice in the one in the second direction, we have to flip it too, because we wanted to satisfy condition number 3. So yeah, we want to have everything be less than or equal to. What about number 2? How do we deal with variables that don't have constraints that they're greater than or equal to 0? We have a lot of variables. How can we change our variables to end up with a situation where our variables are all greater than or equal to 0? We might have different sets of variables. We could separate it in different cases, but there are 2 to the n possible ways to flip signs. Absolute value is going to make our lives really painful, so let's not deal with absolute value. As you saw in the previous problem, we had to take an absolute value and convert it into a set of things that weren't absolute values in order to be able to use. Think about it as a polytope. So what we're just going to do is, this sort of seems like cheating. We can just replace x1 by x3 minus x4, for example, with x3 and x4 both being non-negative. That will capture every possible x1. We can go easily either direction. If we substitute in x3 minus x4, we end up with this. And x3 and x4 are both greater than or equal to 0. So like the optimum for one is going to be the optimum for the other, and we can easily convert between the two. Questions? It's just a way to take an LP and to change it into an LP that has this nice standard form. Can we express those inequalities with slack variables? Yeah, we absolutely could. We can talk about that later, next class. Okay, so let's look at the dual now. Suppose we have an LP in standard form. Max, all less than or equal to, with the exception of all the variables being greater than or equal to 0. We can work out some things about the optimum. Let's add the first inequality constraint and 2 times the second. So here we have this inequality constraint and twice this. So on one side, we have 4 plus 2 times 10. On the other side, we have this plus 2 times this. So we have 24 is greater than or equal to this. This is the case for any feasible x. Now we have something nice here. Why does this help? If we knew exactly how to add these together to give this. Why is this helpful? Why does it help us know anything about this LP? It's not quite the same as the equation we're trying to maximize. If it were the equation we were trying to maximize, we could say, OK, well, this max is going to be less than or equal to 24. But it's good still because we know that x2 is greater than or equal to 0 here. So this thing that we're trying to, this thing that we've gotten, we know it's greater than or equal to the thing we're trying to maximize. And so putting that together, we know that the optimum here is at most 24. OK, that was this really special case. We know that the maximum is less than or equal to 24. How can we generalize this? So what we're going to try to do is we're going to try to take a linear combination of the constraints in this LP to see how tight a bound we can get. Let's multiply the first constraint by y1, and the second by y2, and so on. And then we're going to add them together. Now, what do we get overall? If the coefficient of xi in constraint number j was aij, and the coefficient of xi in the objective is ci, then we want to combine these to get something where the coefficient total, which is this, on xi, is greater than or equal to the coefficient in the objective, which is ci. So before, what we had was we had the coefficients being 2, 2, -1. And that was good because 2 is greater than or equal to 2, 2 is greater than or equal to 1, and -1 is greater than or equal to -1. So we're just trying to find some ways to multiply, linearly combine our constraints to get something that in each coefficient is greater than or equal to the objective. Now, obviously, we also want all of the y's to be greater than or equal to 0, so we don't flip these inequalities. And the bound that we get is going to be the linear combination of these, where the bj are upper bounds in the inequalities on x, which are 4 and 10 in this case. So we get a combination of 4 and 10. In this case, we had 2 times 10 plus 4. Do we need to use all the constraints? No. Some of the yj's could be 0. Yj is greater than or equal to 0. It's just like any way we want to combine them. This will be a way to get our upper bound. And we want the upper bound to be as small as possible, so it gives a good upper bound. So putting all of that together, and we're going to see, I'll finish next time, putting it all together, what we're trying to do is we're trying to minimize this upper bound. But we need to make sure that all of these work out. So for each of the variables xi, we have that this combination of coefficients from the constraints is greater than or equal to the corresponding coefficient in the objective function. So what we have is we have an LP. We're trying to minimize this thing, which is a linear combination of the y's, subject to this and this. We'll come back to it next time, but if you have a general LP in standard form, if you had max of this objective such that ax is less than b, equal to b, and x is all non-negative, then the dual can be written as, this is exactly what we wrote on the previous slide, just saying that we're trying to minimize this combination of the b's subject to the constraint that A transpose y is greater than or equal to c, and y is greater than or equal to 0. Now, next time, we will show why the dual is important. And we've already seen basically why this thing should give us an upper bound on this thing, but we will prove that more formally. And then we will look at how to actually solve linear programs. I'm happy to stick around for a bit for questions.